Hi, everyone. My name is Dzejla Tahirovic. I'm a VP of Data at Social Explorer, a location intelligence company. My today's talk is going to be about read and write optimization in modern database infrastructures. I'll share a little bit about myself first. Actually, I originally come from the academic world. I completed a PhD in computer science at Stony Brook University, and I worked in academia for the subsequent 7 years. During that time, I co-wrote a book on massive data algorithms and data structures. The goal of this book was to bring this sometimes advanced and theoretical topic closer to practicing data engineers and data scientists. 3 years ago, I made a switch to industry, and now I serve as a VP of Data at Social Explorer. My publisher, Manning, has specifically for the attendees of this conference created a discount code for all of their books, including this one. It's 50% off until June 30th. Alrighty. So my today's talk is specifically going to be about data structures that underlie different database technologies. I believe that most of you watching this talk use many of these, or at least one of these technologies on a daily basis. And there's actually a really exciting line of research that I was able to be a part of and kind of learn about and in some modest way contribute to back when I was a PhD student, that is related to data structures on disk and indexing and kind of different trade-offs that exist between these data structures and how those trade-offs translate into trade-offs between these tools. So why should you learn about things like that? I doubt that you're going to walk away from this talk wanting to build your own database engine. If you do, that's awesome. But the fact is that many of us are facing scalability challenges in our everyday tasks. And you don't really need to work for, one of the big 5 companies that deal with petabytes of data in order to encounter those challenges. In fact, it is quite more often the case that companies with more modest and limited resources, that engineers at those companies need to find more clever ways to solve problems within those limited constraints. And my hope is that understanding more about data structures that live under the hood of these database systems can help you choose the correct one for your use case. So what are we going to be talking about today? We're going to be starting from read optimization, so lookups, how fast the lookups are. And as a kind of a representative data structure there, we're going to be talking about B-trees, the optimal data structure for read performance. And we're going to be moving more towards write optimization, so the high ingestion data structures such as LSM-tree. And B to the epsilon tree is going to be kind of the happy middle between those two worlds. Just a caveat, I believe each one of these data structures deserves a much longer talk. So my hope is just to introduce an overview, a silhouette, main ideas behind these data structures, and I'm definitely going to leave out many very important details. Before we begin, what I believe is important to talk about is how are we going to measure the performance of these data structures? So basically, how are we going to be comparing which one is better at what? And to do that, we're going to be using the I/O model. And the I/O model is really good at capturing important aspects of computer performance. So when data sits on disk, the disk will be considered to be of infinite size, right? And in order to do anything with data, you need to bring it into the main memory here. And once you bring it into the main memory, the operations run really fast. You can do billions of them. However, data is transferred in the blocks of size B, and there are contiguous blocks laid out on disk. However, you can only do thousands of those, depending on kind of whether you're using solid state drive or magnetic disk or whatever. But either way, there's a big gap between those two levels of performance. So effectively, we're going to consider everything that happens in main memory to be completely free, even though it's really not. And we are going to be measuring this performance bottleneck, basically. How many IOs does a data structure or operation needs to do in order to complete a task? So we're going to be talking about IOs. So let's get started. B-trees, I believe most of you have heard about or learned about at some point, and they're really the most ubiquitous data structure used in database systems, in file systems, and it's been around since 70s. For example, the table data in MySQL, DB, is a B-tree. And what a B-tree is, it's a search tree where node is the size of that block that I was just mentioning. So that can be 64 kilobytes, it can be 1 megabyte, it can be even bigger. So if you do the math, if you have, let's say, 64-bit keys, one block can fit thousands of keys, right? So a node will have thousands, sometimes even more, keys inside of itself. So basically, B-trees are going to be shallow and wide. Every node of the B-tree is going to have on the order of B children, which basically means thousands of children. So as you go down the levels, 1 becomes 1,000, becomes 1,000,000, becomes 1,000,000,000. If you do the math, it becomes pretty clear that B-trees are never going to be too deep, right? Maybe 5 or 6 levels or 7 levels, depending on what's the block size that you chose for a B-tree. And all the operations in a B-tree are actually going to, in the worst case, going to go down to the bottom of the tree, the lookup, the insert and delete, and we are going to apply inserts and deletes in place. Okay. Now, what that's going to mean is that the cost of operations in a B-tree is going to be directly related to the depth of the tree, which is log base B of n. This is not that cheap, considering that if you can do thousands of IOs per second, and you need to do 5 IOs for one operation, that means you can do about hundreds of operations per second. That's not that fast. However, as it turns out, this is optimal for searches. So B-tree is designed to be giving you the best possible block it could be giving you with the knowledge that you have to kind of further route your search. And a B-tree is going to be great for systems where you don't frequently change data, but you have a big database of data that you frequently query. However, as it turns out, not only is it possible to have a data structure that has better inserts and deletes than a B-tree, but it is also possible to do it by not sacrificing the lookups, right? At least talking asymptotically, right? So what's that data structure? That data structure is called B to the epsilon tree. And what B to the epsilon tree is going to be about, it's going to allow a more laid back approach to inserts and deletes. So what are we going to do is that this node here, which, for example, here we have B is 16, so we have space for 16 things. Instead of filling all of the node with the keys, like in a B tree, we're going to only have a couple of keys. Here we're going to have 4 keys in this example, and the rest of it will be saved for messages, insert and delete messages that are temporarily going to stay there in some kind of a buffer, and as they travel down to their appropriate leaf. So these insert and deletes are going to be a bit more relaxed, right? Like, who's going to know whether you in place inserted or not, right? You're only going to know at the time of a lookup whether you correctly inserted or deleted, and so on. So basically, that's an important insight here, that inserts and deletes become these messages that are in some way delayed. So what happens here, so we have a full node in this example. We have 4 keys and we have 12 messages. And as you can see, there are these like gentle boundaries between these sub buffers, right, that go in different directions down the tree, but everybody's sharing the buffer, right? So we're only looking at the total buffer size of 12, and until you have more than 12, you're good. So now we're getting a 13th message, which is delete 8, which is destined in this direction B, right? So what we're going to do at that point, we're going to look for the fullest subbuffer, which is D at this point. It has 4 messages, and we're going to flush it, right? So when we flush this subbuffer, it's going to go to the appropriate child node, and those messages are going to go in appropriate subbuffers, and we'll be able to store delete 8 into the parent node. So what's cool about this? What's cool about this is that now you have 4 messages that are traveling together. They're kind of carpooling in the same IO. So they are actually, one item is paying 1/4 of the cost of IO instead of paying one entire IO for just itself, which is what we had in a B tree, right? In a B tree, you're kind of rewriting the blocks over and over and over again just to change one element in them, and that's not very efficient. Now, you might wonder, well, how are we going to make lookups work, right? Because you have all of these inserts and deletes all over the place in the tree. Well, every insert and delete message are tombstone messages. They have a timestamp next to them, right? So a lookup query basically will be going down to the bottom of the tree, and on its way to the bottom of the tree, it's going to have to encounter all of the insert and delete messages, right? And their timestamps. So here you can see that something got inserted at 0.0, then it got deleted at 14, and blah, blah, blah. And basically here you can ascertain that 7 is present in the data structure. So lookup can reconstruct this whole history. So this is kind of a nice little trick with having buffers in a node. But to kind of get the maximum performance benefits, you need to very cleverly balance how many keys you're going to have and how much space for the buffer you're going to save. And the data structure is called the B to the epsilon tree because you have B to the epsilon keys and B minus B to the epsilon buffer space. And as it turns out, the best choice of epsilon is 1/2, right? So when epsilon is 1/2, then you basically have square root of B keys in a node, and you have B minus square root of B space for the buffer. Now, why is this a kind of a sweet spot? Well, it's a sweet spot because square root of B keys is only going to give you a tree that's twice as deep as the B tree. So still asymptotically log base B of n depth. On the other hand, B minus square root of B buffer size is still order of OB, right? So you're still going to be able to fill these sub-buffers sufficiently. How much? Well, in the worst case, every sub-buffer is equally filled when you're flushing, right? That's the worst case, which means that order of B divided into square root of B compartments gives you square root of B elements. So square root of B elements are getting flushed in one IO, and the cost per element is 1 / square root of B. I hope this makes sense. So what that's going to give us when it comes to the insert and delete performance is this reduction in the factor of square root of B. Now, this might all look like, a bunch of math gymnastics, which to some degree it is. However, in practical terms, if you think about B storing thousands or millions of elements, then that's going to give you performance of 10 to 1,000 times faster, right? And it's possible to verify this empirically. On the other hand, what's hidden in here with lookups is a factor of 2. So lookups are going to be twice as slow as in a B tree. B to the epsilon tree is not as popular as a B tree. It hasn't been as widely known, and it wasn't, invented in 70s. But it has been implemented in some recent database and file systems, such as fractal tree in TokuDB. That's a B to the epsilon tree with a number of optimizations that, matter in the real world. in some prototype file systems, such as BetterFS. And generally speaking, B to the epsilon tree is great in systems that need the balance between good lookups and inserts. For example, when you have an insert that contains an embedded lookup, like insert this element, but only if it's not there, right? So you can forget about having a fast insert if your lookups are going to be bad. Alrighty, so that's about B to the epsilon tree. However, when we talk about blindingly fast writes, we are not going to be, we're not going to want to settle with a B to the epsilon tree. We're going to be wanting to implement something like an LSM tree. A number of database systems and storage systems have implemented it, such as Dynamo, HBase, ScyllaDB as well, Apache Cassandra, LevelDB. A number of really cool products have LSM trees in them, and there are many different variants of LSM trees. And I'm going to briefly, briefly cover the basis of LSM trees. In order to design such a data structure, first, let's completely forget about lookups. Lookups don't matter, right? So how are we going to have super fast writes? Well, logging is one answer, right? So what you can do is you can basically fill the memory with, let's say, key value pairs, sort them, flush to disk, fill another chock full of memory, sort, flush to disk, and so on and so forth. So that's going to give you an optimal write performance, right? So 1 over B, that's ideal. On the other hand, lookups are not going to be great because you have to look through all of the tables, so that's linear, but you can implement a little search or do binary search given that you have sorted the data on top of tables, so you can make it a little bit better. But you can make it even more efficient using Bloom filters. Bloom filters are actually one of the chapters in our book. They're really cool data structure. And they are compact data sketches that basically you can store in RAM to save you a disk lookup. So here we have an example of these sorted string tables that are on disk. There are 50 of them. And for each one, we have a tiny, tiny Bloom filter in main memory. So let's say you have a case where, for example, in Twitter, you're looking up a user ID and you don't know in which sorted string table it is. So Bloom filter will tell you in which tables it might be in, right? So it may make a mistake, right? If you go to 3 and it says, oops, actually it's not there. But then you go to 50 and it says, yes, it's there. But if it tells you it's not in there, like in the cases of 1 and 2, then you don't need to bother checking. It's telling you the truth. So Bloom filters are pretty great. The issue, however, is if you want to keep this false positive rate under control, these Bloom filters are going to grow with the data set. So it's not really tenable to be just flushing these tables indefinitely to disk. So the second improvement that's going to help with that is if we actually, and that's actually going to be an LSM tree in essence, is if these components, which I have here as triangles, are of exponentially increasing size. So one is in memory, of memory size. The next one is also memory size. The third one is twice the memory size. Then you have the fourth for memory size, and so on and so forth. You can do other factors. You can do 3 times, 4 times, and so on. And what this picture here shows is what happens when these components get filled, right? So they get merged and compacted occasionally. So here you're doing a merge of the C0 into C1, but then that happens to trigger at that very moment merge into C2, and then that's going to trigger a further merge. You can have different data structures representing these components. The only thing that's really important there is that they are easily mergeable, because you want to do merge operation like in merge sort between components, because that's going to be sequential read, and that's something that works very fast on disk. One of the issues is if you have a factor where tables grow by more than 2, you're going to be writing the same component many times. So here you're going to have a logarithm of n over m levels, base f, but then you're going to have f over b times that when it comes to the insert, because you're writing, in order to fill a component that's 4 times bigger, you need to write 4 times to it per level. And lookups is going to be not that great here because you need to check every component in the worst case. However, there are things you can do to help both. One is with inserts, you can organize an LSM tree differently. It's called tiering merge policy. The previous one was called leveling merge policy. And it can help you with write amplification. Basically, instead of having one component that's 2 times bigger, you're going to have 2 components of the kind of same size. So you only write once and you never modify something that was written once. So that's going to help you get rid of that f over b. It's going to become 1 over b. And kind of to summarize how LSM-tree works, you're getting this kind of, for insert and delete, you have number of levels, which is log base f of n over m, which it can be log base 2, 3, 4. But then you're dividing that whole cost by b, and that's something that makes it really fast, faster than the previous 2 data structures. On the other hand, lookups have to do with kind of number of levels, so that many IOs. However, Bloom filters, again, can help this go down to virtually big O of 1, right? If you have a Bloom filter that helps you eliminate unnecessary components, you can also make an LSM tree this kind of a happy middle, just like a B to the epsilon tree. And that's about it. To summarize, kind of what are the main ideas from the talk is B trees are hard to beat when it comes to lookups. Delaying inserts and deletes really helps write optimization. You can do that in some different ways. And Bloom filters are great and are used and should be used everywhere. All right. I hope you stay in touch. Thank you for listening to my talk.